Differential equations, growth and decay. Exponential growth and decay model. The formula for exponential growth and decay is shown here. We have y is equal to c times e raised to the k times t, where t is the time, c is the initial value of y, and k is the proportionality constant. Whenever k is a positive number, we'll have exponential growth, and whenever k is negative, we'll have exponential decay. Let's go over some examples. Example number 1. Suppose that 10 grams of the plutonium isotope was released in the Chernobyl nuclear incident. How long will it take for the 10 grams to decay to 1 gram? Whenever we are looking at radioactive decay models, radioactive materials are measured in terms of their half-life. The half-life is the number of years required for half of the atoms in a sample of radioactive material to decay. So here's a chart of some radioactive isotopes. For our problem, we want the half-life of plutonium. From the chart, we can see that the half-life of plutonium is 2.4 times 10 to the 4th power years, which is the same thing as 24,000 years. Here again is the exponential growth and decay model. Y is our function, which represents the quantity of our material. In this case, y is going to represent the amount of grams of plutonium. What we want to do first is solve for c, which represents our initial value. The way we solve for c is by using our initial conditions. Our initial conditions is what we have before anything starts. What that means is that our time will be 0, since nothing has started yet. Also, before anything starts, we know that we have 10 grams of plutonium, which is our y value. Let's substitute our values for the initial conditions. What we have now is 10 is equal to c times e raised to the k times 0. Simplifying, we'll have 10 is equal to c, since e raised to the 0 power is 1, and 1 times c is just c. Therefore, c is equal to 10. You may be thinking, couldn't we skip this step since we know that c is equal to our initial value? In this case, you would be correct. However, in other examples that may not be the case, so it's always better to do this step first. Now that we have our c value, our exponential growth and decay model can be written as y is equal to 10 times e raised to the kt. Step 2 is to find our k value, which is the proportionality constant. To find k, we need some more conditions, and this is where the half-life of the isotope comes into play. We found from the chart earlier, the half-life of plutonium is 24,000 years. What this means is that the time it takes our quantity of plutonium to be reduced by half is 24,000 years. Therefore, our half-life conditions are time is equal to 24,000 years, and our quantity is 1/2 times 10, which is 5. Let's substitute our conditions into our model. Now we have 5 is equal to 10 times e raised to the k times 24,000. To solve for k, first we divide 10 to both sides. That will give us 1/2 is equal to e raised to the 24,000 times k. To bring down our k value, we take the natural log of both sides. We will have natural log of 1/2 is equal to 24,000 times k, since the natural log of e is equal to 1. To get k by itself, we divide 24,000 on both sides. From here, we're going to have to use our calculator, and when you type this in a calculator, what we get is that k is equal to approximately negative 0.00029. Now we have our c value and our k value. Our exponential growth and decay model can be written like this. The question is asking us to find the time it will take for 10 grams of plutonium to decay to 1 gram. We can now use our final conditions where the quantity is equal to 1 gram. Substituting 1 gram for y, this is what our equation will look like. From here, all we do is solve for t. When you solve for t, you're going to get that the time it takes for 10 grams of plutonium to decay to 1 gram of plutonium is approximately 79,726 years. In this example, I'm going to go ahead and change up the format. I'm going to be using my tablet here. In the comments below, let me know what format you prefer better, whether you like the first example or if you like this one. Anyway, example number 2. Suppose an experimental population of fruit flies increase according to the law of exponential growth. There were 100 flies after the second day of the experiment and 300 flies after the fourth day. Approximately how many flies were in the original population? What I want to do first is write down all of the conditions that I know. The first set of conditions they give us is that there are 100 flies after the second day. So that means when our time was equal to 2 days, there were 100 flies, which is our y value. And remember, y is always going to be the quantity. Next, we were given that there were 300 flies after the fourth day. So that means when t was equal to 4 days, our y value is equal to 300 flies. And now, let's go ahead and write down our exponential growth and decay model. Remember that it's y is equal to c e raised to the k times t. For both of these sets of our conditions, I'm going to go ahead and write down our model for that. So this first set over here, y is equal to 100, and that is going to be equal to c times e raised to the 2 times k, since 2 is equal to t. Now on this side, we're going to do the same thing. Y is 300. That's going to be equal to c times e raised to the 4 times k, since t is 4. Now in both of these sets, we know that our c values, right over here, they have to be the same. And also our k values are going to be the same. So what I want to do is I want to set both of these equations equal to c. So I want to solve for c on both sides. So let's look at the first one. If we were to solve for c or isolate c, what we'll have is that c is going to be equal to 100 divided by e to the 2k. All we did there is just divide e to the 2k to both sides. And if we do the same thing on the other side, what we'll have is c is going to be equal to 300 divided by e to the 4k, like that. Now what we can do is go ahead and set these equal to each other. So that means that 100 divided by e to the 2k has to be equal to 300 divided by e to the 4k. From here, what we have to do is solve. What I'm going to do is I'm going to move that 2k over to the other side and the 300 over to the left-hand side. So what we'll have is 100 divided by 300 is going to be equal to e to the 2k divided by e to the 4k. From here, let's go ahead and simplify and solve for k. The left-hand side will become 1/3, and that is going to be equal to e to the negative 2k. From here, I want to go ahead and bring the k value down, so we have to take the natural log of both sides. So ln of 1/3 is equal to negative 2k ln of e. And we know that ln of e is just equal to 1. So now I can divide negative 2 to both sides, and we'll have that k is going to be equal to ln of 1/3 divided by negative 2. And when you type this into your calculator, what you'll get is that k is equal to 0.5493. So now that we have our k value, we want to solve for our c value. And what we can do is write our exponential model, and we can use the same one that we wrote before for any of the conditions. So I'm going to go ahead and pick the condition right here, 100 flies after the second day. So writing down our model, we have y is equal to ce to the kt. And in this case, we know that y is going to be equal to 100. And that's going to be equal to c times e k, which is 0.5493, times our t value, which is 2. And now, when you solve for c, we'll have that c is going to be equal to 100 divided by e to the 2 times 0.5493. And now, when you go ahead and type this into your calculator, what you'll get is that c is going to be equal to 33 flies. So the original population of flies in this experiment is 33. This is going to be our final answer. Example number 3. 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. If the sales follow an exponential pattern of decline, what will they be after another 2 months? So first, what we're going to do is just write down our model, which is the exponential growth and decay model, which is y is equal to c times e raised to the k t. Let's go ahead and write down some initial conditions so we can solve for c. So we know at the beginning of time here, t is equal to 0, and y is going to be equal to 100,000 units, because that's what we were given initially. Let's go ahead and plug these in. So we'll have 100,000 is equal to c e raised to the k times 0, since initially time is 0. This value here is just going to become 1, so we have that c is equal to 100,000. Now let's go ahead and write down our model again. We have y is going to be equal to 100,000, since that's what c is equal to, e to the k times t. From here, what we want to do is try to solve for k. And to solve for k, we need some more conditions. And what we know is that after 4 months, the sales dropped to 80,000 units. So our y value is 80,000. That's going to be equal to 100,000 e raised to the k times, and our time in this case is 4 months. So we're going to put a 4 there. And now, when you solve, we're going to divide by 100,000 to both sides. 100,000. And what we'll get on the left-hand side is 0.8, and that's going to be equal to e to the 4k. And now to solve for k, we take the natural log of both sides. So we have ln of 0.8 is equal to 4k ln of e. And we know ln of e is equal to 1. So now we divide 4 to both sides, and we will have k is equal to ln of 0.8 divided by 4. And if you were to type this into your calculator, what you're going to get is that k is approximately equal to negative 0.0558, like that. So from here, all we got to do is now find out what the sales will be 2 months in the future. So we have our k value, we have our c value, and now we want to find our final condition, which is right here, 2 months. So that means that y is going to be equal to 100,000, because that's our c value, e to the k, which we know is negative 0.0558, times our t value. And now what we got to be careful with is our t-value is not going to be equal to 2. Remember that we've already gone through 4 months and we're trying to look 2 months into the future of that. So that means our t-value is actually going to be 6, which is 4 plus 2. So now if you were to go ahead and type this into your calculator, what we're going to find out is that the number of units per month that this manufacturing company will have or will be selling is going to be approximately 71,500 units. So this is going to be our final answer.